All right. Welcome to Data Science Club number 26. I'm about to play what was a pre-recorded interview that we did with Patrick Hall, who's the Senior Director of Data Science Products at the company H2O.ai. I hope you guys enjoy it. It was a really fun conversation, and I know I learned a lot, and hopefully you will as well. And hopefully we'll do more interviews like this in the future. Let us know if you had any questions, and we can always reach back out to Patrick and get some answers for those, or we can see who else we can have on, or what else we can cover. So yeah, without any further ado, here's the interview and Jupyter Notebook that we did with Patrick. Enjoy.
Yeah.
And Ravi is running a little bit late, but he'll join us when he shows up.
Okay.
So how are you doing today?
I'm good. How are you?
I'm doing good. Thanks so much for agreeing to join us on our little Data Science Club podcast screencast thingy.
Sure. Seems like a decent use of time on a Friday morning.
Yeah, we have a lot of fun with it, and kind of use it as a way to help sharpen our own skills, and then also provide a shallow end of the pool for folks that are looking to get into data science things.
Okay.
So yeah, I guess we should just go ahead and get started with to use your time well. Get started with questions, and we'll just kind of see where it goes.
Okay. I do have so I wanted to use that Aquarium environment, which always works, except for it's not starting up this morning. So
okay,
and I can't really troubleshoot it. I can just use a regular Jupyter notebook.
Okay.
And it may just kind of start up in a minute. I don't know. I don't know exactly what's going on.
All right. Well, the other thing that Ravi and I have talked about is that given that you had sent us a few different notebooks, we were thinking that we would, in a couple of future sessions, just go through those on our own as well. Since you said the Aquarium environment is available for academic use.
Yeah, but this morning it's slow.
Okay.
Or broken. I'm not sure which, unfortunately.
Yeah. Well, that's being in a research computing environment. So that's where we're at. So we run the supercomputer here at UAB.
Mm-hmm.
So yeah, we're familiar with those kind of on-demand resources. They always work unless you're trying to give a demo.
Yeah. Well, I mean, it's always worked in the past. I just did a tutorial like in Budapest, and I don't know. It's weird, but yeah, it's not working for me this morning. So maybe it'll come online in a little bit, and if not, I can just use just regular Jupyter Notebook.
Okay. All right. Well, that sounds great. That sounds great. All right. Well, yeah, then I'm going to just start with questions, and then we'll get to the Jupyter Notebook, and we'll just kind of see where it goes. So thanks again, Patrick, for letting us interview you. And so can you just tell the folks that will be watching and listening a little bit about your educational and work background? I know you work with the company H2O.ai, which does a lot of work in the interpretable and explainable machine learning space. So yeah, just a little bit about your education and work background.
Sure. I started out as a chemistry major in undergrad, and did a couple years of that, and then switched over to math, and I ended up graduating with a BA in math and going on to chemistry graduate school, where I studied physical chemistry and computational chemistry. That I just did not love that, but it ended up being really, in the end, it ended up being really good, because it turns out that the math in computational chemistry is very, very similar to the math in machine learning. So
yes.
in computational chemistry, we're always trying to rearrange the atoms until they're in a low energy state.
Yep.
And machine learning, if you don't know, is really just rearranging model parameters until the model is in a low error state. So
yeah, it's just gradient descent essentially.
Yeah, it's really so that just ended up being kind of a lucky coincidence, and I did what a lot of people apparently did, which was get out of physics or chemistry or other hard sciences like that and try my luck in data science, and that's how I ended up here. So I think I did not finish the chemistry degree. I ended up getting a master's in analytics from NC State University a couple years back, and I worked at SAS Institute, which is they're a large analytics software provider based out of North Carolina, and then I worked at H2O, and now it's here. Now.
Yeah, and so you're the senior director of product there at H2O?
Yeah, that just means I'm not a very good engineer, which is true. So I help direct the product by, essentially research efforts and interfacing with customers and think tanks, because the explainability stuff has so much to do with regulation. There's a lot of sort of communication with these kind of pseudo-regulatory think tanks, and occasionally regulators themselves, and of course customers. A lot of working with customers to get things right. So yeah, that's what I do.
Yeah, so you're very kind of externally facing.
About half and half. I spend a lot of time working on prototypes and writing papers and stuff like that, and then probably about half the time out in the world talking to people, doing stuff like this.
All right, excellent. Well, we're certainly happy you could have the time to do this kind of stuff with us too. So would you say that that's par for the course though with data science, is that there's a lot of interaction with people involved with doing the data science?
I think to be successful, yes. And I think it also depends. So one thing is, I do write a lot of papers, but they're not really research papers, right? They're very practically oriented papers. A lot of best practices type things, and so, yeah, I think if you're not a pure machine learning researcher, which actually very few people are, then yeah, you do need to be out there interacting with the people who are going to be using whatever data or machine learning product you might be making.
Cool. All right. So let's see. It seems like you kind of started doing data science more in name once you moved into the graduate program in that master's degree that you said that you moved into. So when it seems like you're also doing a lot of stuff with machine learning interpretability and explainability.
Yes.
And I've heard that those are two different things. So,
well, yeah, some people
say they're
people have differing opinions, and I try to respect those opinions. There is an effort to make directly interpretable, like nonlinear, quote unquote, machine learning models. So models that would at least have the capacity to be more accurate than linear models or single decision trees or sort of simple rule-based systems, things that we would generally consider to be interpretable. So there are researchers who work on that aspect, in particular Cynthia Rudin at Duke University and Rich Caruana at Microsoft Research come to mind. And even they have different words for it. Sometimes some of the Caruana papers have said intelligibility, but it does seem like in general that we talk about, like, interpretable is a property of a model, whereas explainable is something that an explanation is something that we do after the fact, and this is just mostly, right? Mostly. And I think one thing that I'm trying to be vocal about is, it might be better to use both of those things together. And using a model form that's directly interpretable, and then seeing what kind of extra information you can get out of it by using some of these post hoc explanation techniques like Lime and Shapley values and things that you hear about on the internet.
Yeah. Yeah, no, that makes a lot of sense. So is that the primary domain that then you're trying to focus on with your data science?
That's definitely what we've worked on really hard the past 3 years or so, and now we're trying to branch out into some different areas, only because we realize that to do this right, who cares if a model is interpretable if it's biased, exhibiting a lot of unwanted sociological bias? Who cares if a model is interpretable if it's wrong? Who cares if a model is interpretable if it's been hacked or manipulated? So I think all of these things, explainability, interpretability, fairness, which is very difficult to define and even talk about, security, and then what we call model debugging. I think they all really are important and don't exist in a vacuum, right? They're all intertangled with each other, highly locally dependent on each other, like in a machine learning model.
Yeah. Do you feel like there is a time coming in the near future where we might actually start implementing Isaac Asimov's 3 rules of robotics into machine learning models once we have a good handle on these, how to interpret and explain our models and build fairness into them?
I don't know exactly what those 3 rules are off the top of my head. I mean,
I don't remember what they are off the top of my head either, but basically do no harm to humankind.
Yeah. That's what I have in mind too. And I got a strange email a couple months back asking if my company was making tools that can kill people automatically. Oh, wow. So that was kind of striking.
Yeah.
To which I replied, no. I mean, I hope that's not what we're doing. We just make machine learning software.
Sure.
But I mean, that's okay. So that's a very crucial thing that I'm always on a high horse, annoying people, being preachy about this, is you don't know what your software or the model you train may eventually one day be used for. And so that's a really important thing to think about. And so I would argue, now I Googled the 3 laws and I'm looking at them. A robot may not injure a human being. A robot must obey orders given by a human being. A robot must protect its own existence as long as such protection does not conflict with the first or second laws. So I think we already need the first 2, actually. There's too many examples of discriminatory or sort of otherwise misused or abused machine learning systems. There's too many examples of those things already. Yeah. And so maybe we need something along the lines of the first 2 already. And that's one thing I always try to communicate to people is it's actually not a far off thing. It's already happening today, at least to a certain extent.
So do you think that the unfairness of a machine learning model, does that come in with not having a training data set that's representative of every fact? Or
that's one place where it can sneak in. I always go to pains to say I'm really not a fairness expert or a social scientist in any way. Just certainly one place that unwanted sociological bias can sneak into machine learning models is having unrepresentative data. There are other ways that it can sneak into a model, but I think one thing that even someone who's not an expert like me can communicate clearly is I think there's this, potential misconception that somehow machine learning models make bias.
Mm-hmm.
Machine learning models, as compared to sort of lower capacity predictors like linear models, probably have the ability to exacerbate bias, but models learn from data, and so very oftentimes the bias exists in the data. It would be I think it would be a very rare case for a machine learning model to take bias without unwanted data without unwanted sociological bias and somehow make bias out of it. But it's probably possible. It's probably possible. But I think that's one thing to communicate, is that unwanted sociological bias does come from data, and many of the ways to remedy it involve, just having the right data.
Yeah. So with that being said, I think one of the you had a few different Jupyter notebooks that you had sent us to look at, and I'm going to let you pick whichever one you feel like you want to show this morning.
Okay.
And then, as I said, Ravi and I will probably explore the other ones in some future podcasts, kind of on our own in the next coming weeks.
Yeah, that's great, and I'm happy to answer questions if you guys have any. I'm toying with whether I'm going to show it using the H2O Aquarium environment, which does seem, it was slow this morning, but it seems to have popped up. And if all else fails, I can just show it off my laptop. So let me go ahead and share my screen.
Okay.
Okay. All right.
Perfect.
Let's see here. We'll give this. All right. So this is on Aquarium because it has this Amazon URL. So I'll give this a couple more seconds. It ran one cell, but now it's being a little bit. Okay. All right. So I think Aquarium is going to work. Which it always has before now. Okay. So if you want to follow, if you want to follow along, I'll keep these instructions up. It's pretty easy to get started using Aquarium. The key is, let's see, once you get in, you probably want to go to Lab 7 Open Source MLI, which is an internal abbreviation that we should be a lot more careful with, which stands for Machine Learning Interpretability. That's the lab that we're going to be working on.
Okay.
And once you get that, and again, you can follow the instructions here. And I'm not going to read them to you because I assume that most people that will watch this can read English.
Yep.
And I'm gonna do my favorite recent notebook, which is Disparate Impact Analysis, which of course, Disparate Impact Analysis is sort of a canonical, traditional bias detection tool, and so this notebook has a little bit of everything, which is why I like it. So it has a little bit of the unwanted sociological bias detection. It has constrained machine learning models, or interpretable models, or more interpretable models, and then it also has some of that post hoc explanation. So that's why I like this notebook, because it kind of touches on a lot of different things. So I think everybody is, well, not everybody, but many people are interested in learning more about fairness and machine learning these days. And so I've highlighted some. I'm not an expert. I'm not a social scientist. I'm a technologist. But these seem to be really good resources. So this is a book that's sort of a free book that's being kind of written in public, a lot like the famous deep learning book that came out over the last couple of years. These are packages that just total open source packages that probably make some of the things I'm going to do in my notebook a little bit easier. And then I would say this IBM AI 360 package goes way beyond what's in this notebook. They have all kinds of neat stuff that you can check out for not only checking for unwanted sociological bias, but removing it either by pre-processing data, training models which somehow consider fairness as their training, or post-processing your model decisions. So this is a really interesting package that I urge people to check out, and all three of these are really all three of these represent really nice work that was done either in the commercial or academic community. All right, so I honestly don't even know what this cell does. It's something that lets us do port mapping, so don't worry about that. And now we're going to import some of the software that we're going to use. So I think the most interesting things here are we're going to use H2O, which is, they're my employer, but in this case, it's also just a completely open source piece of software. We're going to do, and feel free to jump in if you have questions. So we're going to train a gradient boosting tree model. So
okay,
a tree ensemble model.
Is that similar to XGBoost?
Mm-hmm. Yeah, it's just, so my friend Sillard Pafka, whose Twitter handle is Data Science LA, he's got to be the world's leading expert on applied gradient boosting, and he has all these detailed sort of recommendations of when you might want to use H2O versus XGBoost versus like GBM. But I think for our purposes, they're all very similar. So yeah, it's very similar to XGBoost.
Yeah, different sizes of Phillips head screwdrivers, but in the same family.
Yes, yeah. And I mean, if you're doing something really serious, you should go look at Sillard's work and get a good sense for when to use which library. But generally speaking, they're very similar. Then this SHAP package, I'm also a huge fan of the work of Scott Lumberg at the University of Washington, and now Microsoft Research. And this is the package that has his new tree SHAP and other sort of Shapley value work in it. So, but again, totally open source. So I think those are the only sort of notable things to call out here. Everything else is just meant to be very, very standard Python packages. Mm-hmm. All right, so one thing with H2O is we imported H2O, but then we have to initialize H2O. So one thing to realize about H2O that is different than XGBoost is H2O is both a library and a server. And that's where some of the magic of H2O comes in, is that it's very native in the Hadoop ecosystem. It can run across multiple machines very easily, and that's because there's this Java software server in the background that's sort of managing all the complex stuff that's going on that makes H2O fast and scalable. So that's just one difference between H2O and XGBoost. After I said they're generally the same, is H2O is both a library and a server. And that means that we can talk to the server with R, with Python, with Java, with Scala. So probably everything I'm going to show today could also be done with R if there are people out there in the audience, which there often are. So I'm going to use this Taiwanese credit card data set that's available on Kaggle and the University of California Irvine Machine Learning Dataset Repository. It's a really, really simple data set and small, but it works for our demo purposes. So basically we have demographic variables about people, which we won't use in the model today, because that's one way that people think that you can train more fair models. And then in just one way, right, people argue or have differing opinions about that. And then also in the context of credit lending in the United States, it's typically just frowned upon or even illegal to use variables like this in your model. So we do have these demographic variables, and we'll use them later to test for unwanted sociological bias. And then we have things like their credit limit, their repayment statuses. So this is a categorical variable that essentially says, they paid in full, they left some balance on their revolving account, They were 1 month late, 2 months late. So basically, lower is better and higher is worse.
Okay.
For these repayment statuses. Bill amount is just a numeric variable. It's their billing amount. It's how much they were billed, and then payment amount is how much they were paid. They paid towards the bill, and it's all across 6 months. So pay 0, bill amount 1, pay amount 1. That's the most recent information we have. Going back to pay amount 6, bill amount 6, pay 6. That would be the information from 6 months ago. And I get another slight difference between H2O and XGBoost would be that H2O accepts character inputs directly, which doesn't usually matter in a Kaggle contest or something like that, but it is really nice out there in the real world. Okay, so I'm just going to read the data in, briefly assign some modeling roles. So we're going to be trying to predict whether someone defaults the next month. And that's a 1-0 binary target in the credit card data set. And we're going to use these variables as inputs. We're going to use all the payment information that we have as inputs.
Sure.
And not the demographic variables. And, you know, credit limit is probably questionable whether to put that in there or not. It's kind of, it could potentially leak information because credit limits are a way that risk is priced in. But just for this kind of small, and in the context of adverse action notices, like in the more regulatory context, I probably can't use that as an adverse action notice. I can't tell somebody I'm not giving you more credit because I gave you a low credit limit, right? The spirit of the regulation is to give people reasons that they can appeal, right? So so I can't, that's why I can't say you're too old for a credit card, or you're too young for a credit card, or I've given you this credit limit that I'm not allowing you to change, and that's why I'm not extending your credit. So just a caveat. Let's see. This is like I said, H2O does accept character variables. So this is just to recode the data. So it looks prettier that it actually has some of the character levels in there.
Yeah. Does it, in the back end, is it just one hot encoding those characters, or is it doing some other kind of encoding?
It does different things for different models. It actually does different things for different models. And it's fairly detailed in the documentation. And
okay.
I'm sure sometimes it does just one hot encode them, but sometimes it does fancier things.
Okay. Yeah. Well, we'll have to check that out when we run through the other stuff.
And sometimes I use XGBoost. I mean, I think they're both really, really solid tools. All right. So this is just to give you some idea of what the data looks like. So this is the first 10 rows of the data. So we can see credit limits. They're in, I think, new Taiwanese dollars is the currency. So they're a little bit higher than they would be in terms of American dollars. But they run roughly from 10,000 to 1 million Taiwanese dollars, the credit limit. And we can see here's those repayment variables and the billing amounts, payment amounts, and our binary target that we're going to try to predict. I'm going to do a unrealistic, super simple 70-30 validation, training validation data split. You probably want to do cross validation or have an actually workable validation strategy if you're going to do something in the real world. But just, for our silly little example, we'll just do 70-30.
Okay, sure. Train
test or train validation. Okay. Now this is where I'm going to put constraints on my GBM model, which would typically be a black box. Or somewhat of a black box. I'm going to put constraints on it using prior knowledge or business domain knowledge to make it more interpretable. And what I'm going to do is I'm going to look at the Pearson correlation between each input variable and the target. Okay, so these are the variables that I'm using as inputs to my model. And then these are the Pearson correlations. And if it's negative, I'm going to say, or I guess Bill, credit limit is the first example. So if it's negative, I'm going to say, as credit limit increases, the model output, the probability of default can only decrease. And that sort of makes sense, right? If we give somebody $1 million credit limit, we're doing that because we don't expect them to default. Pay zero is sort of the opposite, where, you know, I was saying that higher is worse for pay zero. So as pay zero gets higher, we expect somebody to default. So I'm going to encode that into the model directly and say, hey, as pay zero increases, I only want the model output, the probability of default to increase. And so the way we do this in H2O is we create a Python dictionary that has the name of the variable and a -1 or a 1 for negative monotonicity constraint, positive monotonicity constraint.
Mm-hmm.
And then we pass it in here. And we're already done training. And a lot of times people, you know, I guess my views are pretty okay, so before I talk about that, I should say, if you are going to use monotonicity constraints in your machine learning models, which I think is a great idea, you probably do need to constrain every variable in the model, because if you don't, and let's say you constrain an important variable and you leave an unimportant variable unconstrained, then very likely the model will just force some of the signal from that important constrained variable onto the unimportant unconstrained variable, and it probably won't affect your model accuracy, but it will make like the partial dependence or ALE or ICE, like the functional form of the model, will be really hard to understand because it's essentially pushing signal from one variable onto another variable. So if you're going to do monotonicity constraints, like you should probably constrain all the variables. That's actually a pretty big constraint, and oftentimes people ask me, is there something you can do to not do that? And if it is, you know, I would say yes, and I would check out these GA2M models. They're highly interpretable and really accurate, and they're available through the Microsoft Interpret library, and they don't make those kinds of assumptions. So I think this is if you can't do all monotonic, which sometimes you obviously can't, then I think this GA2M model is a really good alternative. All right, and sometimes people ask, you know, what's the difference with the monotonicity constraints and without the monotonicity constraints? Let's just look. So AUC 0.77. AUC 0.78 without the monotonicity constraints. Mm-hmm. So I don't think it matters. I mean, especially, and you know, what I was going to say earlier, where I have a fairly radical stance, is for tabular data, I actually don't think it matters at all. I think that the interpretable models, the GA2M, the monotonic GBM, I think they are as accurate as any black box model that you could possibly use on tabular data. And so, so there's really no excuse to be using black box models on tabular data. That's my opinion, and I guess it's shared by some other leading researchers. But you know, unstructured data is different. Unstructured data tends to be more complex and may require more complex models, or may not. Time will tell. Time will tell. So now we're looking at the Shapley values, and this is just a nice new variable importance metric that works globally for the entire data set. And that's what we're looking at here. So we're kind of ranking all of the variables across the entire data set. And then later we'll see how Shapley values are used to make variable importance that are per row, that are different for every row. So that was a huge breakthrough, and the Shapley values are special. We probably don't have time to get into it, but it's not just another variable importance metric, in my opinion. It's really kind of an important breakthrough, but probably, you know, that can be for another time, or for somebody's homework or something.
All right, sounds good.
All right. So, whenever I train a binary classifier, I have to make a decision threshold, right? Like when am I really going to, because the model generates, or this model generates probabilities default, continuous numbers between 0 and 1. And, I have to turn that into a, yes, I think this person's going to default, or no, I think I don't. No, I think they won't default. And so I'm going to use PR, precision and recall. I'm going to, and the F1 statistic, I'm going to maximize F1, which is a good balance between these two accuracy measures of recall and precision. And one time somebody asked me, if I'm selecting the model by AUC, is there a better way to select the cutoff? And I think the gold star answer here is something called Uden's J, which would pick the cutoff that maximizes, at the peak of the AUC charge.
Okay.
But picking cutoffs by F1 is really standard. It was a good question. The person who asked that question, that was a good question. I had to think about it for a while. All right. So basically, I'm just going to pick a cutoff. Our F1 statistic is maximized at a threshold of 0.27. So above 0.27, we're going to say they're going to default. Below, we're going to say no, they're not. And these cutoffs actually can impact the disparate impact characteristics of the model pretty dramatically. And so we'll see later that probably this cutoff is a little bit too conservative, and we might want to go back and be more careful about it. But I think the point I'm trying to show is I'm just following a well-known machine learning best practice, selecting a binary classifier cutoff by using F1 statistic, and we'll see later that that's actually a little bit problematic. And here's just we're taking a good balance between high precision and high recall when we take that cutoff at 0.27. So to get into the basic bias testing stuff a little bit, we need confusion matrices, and confusion matrices are always confusing. It's basically a measure of true positives. So these are people that did default, that we said would default. These are people who we said would default but did not default. These are people we said would not default but did, and these are people that did not default and we said they would not default. So true positive, true negative, false positive, false negative. And basically what we want to make sure is that our model is both balanced in its accuracy we're going to check across genders. And so we want to make sure that our model is both balanced in its accuracy across genders and in its errors across genders. And so the first step will be to look at the confusion matrix for men and for women, right? And does anything in particular jump out at us? And so here's the confusion matrix for everyone. And then this is just the same data, but sliced up by men and women. And so right off the bat, the only thing I'm noticing is that which one is this? This is false negative and false positive. The rates look really similar for women and a little bit more different for men. So we'll have to look into that and see if that does end up being a problem. So again, this is one of those places where, I was saying this is a real issue today. Credit lenders have been using predictive models probably for decades. I'm not 100% sure, but I think for decades. And so if I don't give someone a loan incorrectly, that's essentially a false accusation of financial impropriety, right? That it's a big deal. And if I do give someone a loan incorrectly, like two things are going on there. So And okay, so I think one thing I've learned from both sort of the fairness and security aspects of machine learning is there's always two sides to the coin, right? If I don't give someone a loan that they would have paid back, then, and I think that's a type 2 error, then
it's a lost business.
Yeah, it's lost business for me. So it's lost fees and interest for me. And so it's an opportunity cost for me, and it could be and it's like an accusation of false impropriety to the person who I made that decision against.
Yeah.
So but on the other side, if I miss that someone's going to default, one, I'm writing off a ton of money, and two, I'm giving money to someone, assuming that I don't have infinity dollars to lend, I'm giving money to someone that I could have given to someone else. And so both of these type 1 and type 2 errors have two sides to them, right? They hurt me, and they hurt the outside. They hurt people outside of the company in different ways. There are a lot of metrics that are used for assessing the fairness of a binary classifier, and this is only some of them. Actually, this isn't even all of them. This is just ones that are easy to calculate using the confusion matrices. We'll focus on adverse impact ratio, AIR, and then I think we're going to see that we have we're going to see that one of these other metrics pops up as being a little bit problematic, and I can't remember exactly which one, but we'll see when we get there. So again, right, we want to know if the model, but in general, right, it's good to test a lot of things if you're seriously concerned about this. Now, this isn't, what I'm saying isn't probably accurate in a regulatory setting, but just in general, we want to make sure the model has equal accuracy across groups, so things like true positive rate and precision. And then we want to make sure that it has equal errors across groups, and that, false positive rate, false negative rate. So both accuracy and error, we want those to be roughly as equal as possible across groups without compromising the model too much. And then adverse impact is a little bit different. It's probably the most traditional, well-known metric, and we'll talk about that in more detail in just a second. So I just found it helpful to type out the metrics like this and then try to think through what they mean. And then so I wrote another little helper function that takes those sort of human readable definitions and turns them into panda statements. So that's what's going on here. I wanted to be able to see these and think about these, and then this little helper function turns them into actually executable panda statements. All right. So now what we've done is I'm just using loops and stuff, I calculated these across male and female. So I calculated all these metrics across male and female. All right. And generally speaking, things look okay, right? And we'll go a few steps further than this, but in general, right, we want these numbers to be similar. Mm-hmm. And like I said, we'll see one little fairness problem rearing its head later, but in general, these numbers look okay. That may be because I used that more constrained model, or it may just be that there's not that much bias in this data set. And in fact, it's what adverse impact says is true positive plus false positive. So these are all the people I said would default. These are all the people that experience an adverse outcome. I'm not going to give them the loan. Mm-hmm. And so I'm saying I'm not going to give the loan to about 20% of women and about 22% of men, or 23% of men. So from a very, high level traditional fairness standpoint, I'm giving more loans to women than I am to men. So that's roughly a good sign, but we'll dig into it more. So the way a lot of these fairness tests work is we want to divide them. We take these values, we would call female the reference level, and male would be the reference level, and female would be like the protected class. and we want to compare them, right? I want to see how far female is off from male, how far off a protected class is from what would generally be considered the privileged class, at least in past historical data. And so I want to divide female by male, and we'll get to that in just a second. So if any two of these numbers are different, it's probably the false omissions rate. It looks like at least proportionally that there is some difference from male and female. And so what in the world does that mean, right? That now we're getting into some pretty potentially detailed stuff. So false omissions rate is out of the people in the group the model predicted would not default, how many the model predicted incorrectly would not default. All right, so this is about not defaulting and predicting not defaulting incorrectly. So what in the world does that mean for fairness? So false omissions measures how many customers the model predicted incorrectly would not default out of the customers in the group the model predicted would not default. So we'll have to think through that a little bit. We'll have to think through that a little bit more. But if any of these numbers on the table are jumping out as being different, just proportionally, it might be the false omissions rate.
Okay, so in the false omission, if you have a higher false omission rate, then basically it's saying the model's inaccurately saying that one class is going to repay the loan more frequently than the other class.
Yes, exactly. So that's why people are saying to check all these different metrics, right? Because there's just you might say that these are all different fairness definitions. I'm not trying to go that far, but there's just many ways that bias can sneak into these models because they're really complicated. So we'll I think that's an accurate description, and we'll come back to it in just a minute. But so there's this thing called the Four-Fifths Rule, which is just a rule of thumb, okay? So the Four-Fifths Rule is just a rule of thumb. And it says roughly, and it was delineated by the EEOC, the Equal Employment Opportunity Commission. So it sort of came from employment law. And it basically says roughly that I don't want a decision-making system to treat groups of people more than 20% differently, right? It's a very, very rough rule, but if you don't know where to start, it's not the worst place in the world to start.
Sure.
So basically what we do is we divide the female number by the male number and the male number by the male number. So I just leave this in here because I think it's mildly helpful to see what's going on. We divided everything in this table by the male number because we would consider, female as the protected class and male as the reference class. And so when I do that, I can see adverse impact, which is, generally speaking, the most sort of well-known measurement of this stuff. I can see that adverse impact is at least within the Four-Fifths Rule. It's between 0.8 on the low side and 1.25 on the high side. And basically the interpretation of this here is for every one male that I deny alone, I'm denying 0.88 females. And we would be concerned if that number was for every one male I was, denying 0.7 females, or I was denying 1.3 females. But just from a very basic, high level standpoint, we're going to say that this number is okay. It's within the Four-Fifths Rule. Females are actually slightly favored. So we'll say that this number is okay in my silly little example. Now, false omissions rate is outside of that Four-Fifths Rule, those Four-Fifths Rule boundary conditions, okay?
Mm-hmm.
So just slightly, right? Just slightly. So, we'll keep kind of working through what this means. We'll keep kind of working through what this means. I think that the flag false omissions rate, males may, like I think you said, it essentially means that males may be receiving too many loans they can't pay back. If it's a zero-sum game and there's not infinity dollars to loan, that could be preventing females from receiving loans. So I'd say that this is these are good numbers. These are decent numbers. But if we really wanted to be serious about this, we would need to follow up on this. And of course, if it's like $1 billion lending portfolio, it's probably a good idea to do that. But again, I'm not a regulation expert. You know, the way that this is handled in the U.S. is managed under very strict regulatory guidance, and I don't think I'm being, you know, I'm not representing that process exactly here by any means. So,
Sure.
You know, we've been clued in that there could be some minor fairness issue related to false omissions rate. Everything else looks okay. And right here, I'm just plotting that you know, here's my 4/5ths rules boundaries, and of course, male is in there. They're the reference level, but female is just slightly low for false omissions rate. Okay. Now, you know, we can do all these group parity checks, which is essentially just applying, you know, a binary test to whether these numbers are within the 4/5ths rule. And then also, we can define, and again, there's even more fairness measurements and definitions than what I'm showing. These are just all the ones that are easy to calculate from the confusion matrix. So there are ways to sort of hold our model to an even higher bar. So like a type 1 parity test would be if there was group parity, so males and females roughly similar, with false discovery rate and false positive rate, right? So now we're getting into some combined metrics that are a little bit of an even higher bar to pass. And you can see that like we do pass this combined high bar of equalized odds, but not type 2 parity and not supervised fairness. And so we would say from an overall perspective, you know, we do have some bias issues that we might want to look into. I've had really smart, you know, expert sort of compliance people, I've talked to them about this, and their comment was that this may kind of make people feel like it's impossible to meet all these standards, right? So again, I'm not an expert here. I'm not exactly sure how much of this you would want to be blue, but we can. I think the take-home lesson here is we can go to even higher bars of combined group parity test to test our model if we want to. And we'll actually see in just a minute. I can make all of these blue. It turns out. All right. So there's this really tricky thing it can happen in linear models too. I guess it's just more likely in machine learning models that one word for it might be local bias. And that essentially means that the machine learning model is treating similar people differently. People that we as humans would know should be treated the same. It's kind of putting them on different sides of a decision boundary or treating them differently in some other more kind of complex local way. And all of these tests are sort of based on group averages, and they're not going to detect this problem. So I think that's a really scary thing that needs to be communicated about machine learning is some of this traditional disparate impact testing won't pick up all the potential bias problems in a machine learning model. So how you find local bias is really kind of tricky and kind of an Easter egg hunt these days. I started looking at the residuals, and so these are women who I said would default but did not. So these are women false positives. And I originally thought these 3 people looked really suspicious. Like these are the people I was the most wrong about, right? So maybe there's some discrimination there. And what it turns out is, you know, I'm not saying there isn't discrimination here, but they have a horrible repayment history. 2 months late, 2 months late, 7 months late, 7 months late, 7 months late. And then somehow they go on to not default. So the model really thinks they're going to default.
So maybe they're just genuinely outliers.
Yeah, they're just genuinely outliers. And I don't think anyone with this kind of payment history, I don't think any credit card company would offer them, you know, more credit. And we can't say they weren't discriminated against definitively, but they have a horrible payment history. So it's kind of like, all right, if those people are if those people aren't the people to worry about, then maybe it's the people close to the decision boundary. And that actually makes a lot more sense. So
yeah, I mean, if you're thinking of decision trees where it's drawing those boundaries through your clusters of points, then yeah, it's going to be whoever's closest to that boundary, but just on the other side, that's going to get the negative impact.
Right. And literally, right, we know that a machine learning model can just put somebody who makes $100,000 and somebody who makes $101,000 just on the different side of a decision boundary, or 29,999 and 30,000 on the different side of a decision boundary, when that $1 just doesn't matter. So if we look down here, sort of closer to the decision boundary, right, the decision boundary was about 0.27. And if we look at some of these people, again, all women that the model was wrong about, you know, I think these are more likely, this is more likely evidence of local discrimination. I mean, this person never missed a payment. They didn't use their credit card very much, but they never missed a payment. This person had one late payment, and then, you know, so this is where it gets really tricky, because this person has had some recent late payments. This person has had one late payment, and again, sort of minimal utilization. So it's really tricky. It's really, really tricky. But I think if we're going to be very careful, I'd argue that these are potentially examples of people who are kind of arbitrarily put on one side of a decision boundary, and you know, we should probably be a little bit more careful about picking the decision boundary. So you know, very basic ways to remediate fairness problems in machine learning is, like, as you guys said in the beginning, make sure you have representative data, and then 2, thinking about your decision boundary very carefully. So I'm going to go up and you know, toy with the decision boundary in just a minute. Before I do that, so you know, from a global perspective, from a global fairness perspective, things were looking decent. At least we had this one little flag, you know, to kind of, maybe there is something to follow up on. We were trying to be careful about the whole local bias thing in machine learning, and we looked at the residuals as just one potential way to go on that Easter egg hunt. And we found that maybe our cutoff was just a little bit too conservative. It's arguable, it's complicated, but maybe our cutoff is just a little bit too conservative. And I want to show how that's fixable. But before I do that, I want to get into the local Shapley values. So this is for the highest risk person in the data set. So this is someone that we would not extend credit to, right? I think it's literally this person here that has these bad repayment histories. Yep. So we have this monotonically constrained model, and I didn't get into you know, what that looks like. I'm going to go to another notebook really quickly, or actually just show this picture. So I can graph every variable's behavior in a partial dependence plot like this, and see the monotonicity of each feature in general in this model. It's not in this notebook, but that's something easily that we could have done, and it's done in some other notebooks that you guys have access to. So I have this monotonically constrained model where I can draw a picture of how every variable behaves in the model. I can get this overall variable importance ranking, which I think is really helpful. Just overall, pay 0 is very important, credit limit, pay 2, pay 3. And then for every single person, I can get the actual, and this is where the Shapley values are different. They're the actual numeric contribution of each variable to each prediction. And they're all positive here. They wouldn't always be positive, but this person's data is so bad, and under this model, every single variable is pushing them up towards defaulting. So, and another really nice thing is about Shapley value is they're additive. So they add up to the model prediction. And it happens in the logit space or in the margin space. It doesn't happen in the probability space, but here's a check of, you know, whether the Shapley values sum up to the model prediction, and they do. And then we can go ahead and say for every person, like, I can give the top 3 reasons and little written statements, you know, why why I'm not going to give credit to this person or explain the model's decision. So the most important reason we're not going to extend credit to this person is because they were 2 months late on their most recent payment. They were 2 months late on their second most recent payment. And then the next variable is their sixth most recent payment, where they were 7 months late. And so this is actually really, this is a really good explanation of why I wouldn't give someone more credit. You're late on your most recent bills, and you're late on the farthest one out I have. You've actually never paid me back. You're 7 months late from 6 months ago. So these are really good reasons for why you wouldn't give someone more credit. So I want to highlight, like, this is what you can do with machine learning on tabular data today. I can have a model form that's interpretable, that can be interpretable by all these nice plots and other kinds of descriptions, variable importance. And then for every single decision, I can say, based on the input variables, why the model made the decision. And then moreover, you know, we did a lot of sort of thinking about the basic bias testing for the model. So I just think this makes so much more sense than like using, and nothing against TensorFlow, right? PyTorch, using PyTorch to build, you know, a 17-layer NLP network on this data set. That's silly when you can do something like this. So that's
I think that makes sense, especially for tabular data.
Yeah, for tabular data, yes. Yeah.
I think that makes absolute sense.
Okay, and so if we want to fix our easy fairness problem in this easy data set, you know, just from toying around with this so much, I can move up the cutoff just a little bit, and you'll see what happens. So up here in this cell, so we could maximize accuracy or other sort of metrics to maybe make a better argument at picking the cutoff. But I've just played around with it so much. I know if I just move it from 0.7 to 0.27 to 0.3, all my tests will pass. Let's see. All right, so you know, I know we're right at the top of the time, and we did a little bit of questions as we went along, but if you guys have any questions or comments, you know, in the last 2 minutes, please let me know.
Yeah. No, I mean, this is really cool. Thank you for showing this example. I mean, up until this point, what we've been showing has been just how straightforward it is. And we really haven't gotten into like the TensorFlow stuff yet. Just a little bit for like image processing stuff. But this is really nice because this shows, on top of how easy it is to run these decision tree and gradient boosting models, to extend it to actually give you more information about what's going on inside of the model is also pretty achievable for somebody who might still consider themselves to be in the shallow end of the pool. So that's really neat. So I definitely appreciate you showing this.
And I mean, we have done a bunch of videos on tabular data, but we haven't talked about fairness in any of those data. If you can introduce some bias.
Well, it's a really complicated subject, and hopefully I haven't bastardized it completely. And I would urge you guys to bring on. I can even help you find potentially somebody who is more of a real expert in the field.
Yeah. So that was going to be. I guess the last few questions are more kind of centered around. So if people want to follow what Patrick Hall is doing, I know you just recently released a new version of your machine learning interpretability book. But are there other ways that folks should keep up with you, or other papers that you've just released that you'd like people to check out?
Yeah. All right. So this is a good book. It gets longer and longer and a little bit more and more unwieldy every time, but I am happy with it. And it has a ton of different techniques in it to go and follow up on. And so at some point in this book, we just start literally naming techniques and talking about where you can download them. And that goes on for about 30 pages. And that's probably actually more useful than reading whatever dumb stuff I'm writing. But this is a really good one. these models can be hacked. I don't think it's super. I don't know. It's just something to be aware of. It's just something to be aware of, and it's a really interesting and way to think about machine learning, right? Like I said, I learned there's always two sides to this, right? Everything can be a weapon or a tool, and then when it's used as a weapon, it can hurt me, the model provider, and it can hurt other people that are using the model. So it's an interesting way to think about machine learning, if nothing else.
Well, and like the interpretability things that you're showing are kind of direct defenses against the hacking.
Oh, well, and because they are the attacks too, and so I think that's really the reason they're the defenses is because they're also the attacks. And so that was very eye-opening for me to learn about this thing that I had been working on for so long and that I thought was just so helpful. Could actually be used in a negative way. This is a much more sort of technical paper that we put forward with some best practices and about using explainable machine learning if people are interested. It'll be up on archive by Friday or Monday. I can't remember when. And we're really grateful that it was an accepted paper at this NeurIPS workshop. So
sure, yeah.
We've had a good run this year. We had a paper at KDD XAI workshop as well, and so lots of stuff to go on. And I think to learn more about fairness. So for me, and I've actually been lucky enough to participate in this conference too. But go to this conference, look at the resources. And interestingly, their very first resource is the security of machine learning. And I think that's just, happens to be alphabetical by the person's last name, but there is some interplay here. So this is a great resource to learn more about fairness. And then also, I think just using these packages, and IBM has all these nice tutorials on their website, this book. So yeah, I think there's a lot of resources out there. It's just about, do you have time? And time is always a very precious resource, but if you can make a little bit of time, I think all of these would be kind of rewarding resources.
Okay, that's great. And then I know you're pretty active on LinkedIn. Do you also, are there any other social networks that you're active on if people want to stay in touch with you?
Sure. I am on Twitter. And let's see. I mean, this is me on Twitter. Where am my profile? Yeah. So you can find me on Twitter. You can find me on LinkedIn, and I'm usually pretty happy to talk if I have time. So
Okay. Well, that's great. And then who else should we talk to, or should we try to get to talk to in this kind of, because we're wanting to continue interviewing folks like yourself, because I think that's something that's really beneficial to our internal university audience, but then also to the data science community, to really dig into a Jupyter notebook like this and talk about what it takes to do this data science
stuff.
Well,
I can't be sure that, I don't know about these people's calendars, but these are very, if you can get either of these people on your podcast, then good for you. But these are leading scholars in the fairness field.
Okay.
And then Sorel, I don't know how to say her last name, and I don't know how to say Suresh's last name, but I think either of these two people would be incredible from a fairness perspective.
Okay.
And then I can brag on my friend a little bit. Let's see. So Nick is really an expert on fairness in the regulatory setting, and has some really interesting ideas and proven work that he's done on real life AI systems at real life giant financial services companies. And on the security, all right. And so I keep showing this paper accidentally, but I should just talk about it. This is an excellent paper for practical techniques for explaining NLP models.
Ooh,
and we work with Samir Singh a lot. A great guy, very seminal researcher in explainability. And so he's much more on the explanation, security, model debugging side. And this is a great paper for very practical techniques for explaining machine learning models. And then the paper that I keep trying to show is this one. So I can also say my friend Andrew Burt is a great person to speak to or follow for stuff on the privacy and security side. He's a Yale educated attorney who lowers himself to doing machine learning stuff. So interesting guy with lots of interesting things to say.
Awesome. Well, cool. Are you going to be at supercomputing? Does H2O go to supercomputing?
I won't be because I'm a horrible engineer, but like our CTO is a big, former HPC physicist guy. So there might be somebody from H2O there. I'm not sure.
Okay.
And I would say both, our open source software uses this very specialized Java distributed computing framework, and then the proprietary software driverless AI uses very sophisticated hardware-based acceleration with GPUs. And so H2O is really a high-performance computing company. I just work more on this side of things. So
sure. Yeah, no, we're going to be going to supercomputing here in a couple of weeks. So it's just, if you were going to be there, I was like, hey, we should at least say howdy while we're there.
We might find somebody from H2O, but not me.
All right. Not a problem. Well, thank you again so much for talking to us and showing us the your work in interpretability and explainability and machine learning. This is super fascinating, and I know it's going to be really helpful for the folks that we talk to here at the university and other folks. So
cool.
So yeah, right. Thanks so much.
I try to be useful. All right, you guys have a good day.
Yep.
Bye.
Bye.